Welcome back. This is our last section on random variables, Unit 9 from Khan Academy on the statistics and probability section. Um, this this section is going to cover more expected value problems where we have to really break apart the problems to figure out what the probabilities of each part is and how to complete those calculations. So we're going to learn about how expected value represents the long run average of a random process. When we're calculating these expected values, we're going to use both observed data and probability formulas, and then we'll apply these ideas to real world situations like games, money, risk, and decision making. But our overall goal is to understand how probability can help to predict what tends to happen on average over many repeated trials. So let's take a look at our first example here with uh, empirical probabilities. And our first example with empirical probabilities gives us a table and then some different answer options to look through. And it asks us to choose all that apply. So we're probably going to have to check all four of these to just to see what's going on here. So we have some data here from Tanner. He's an ultimate frisbee player. He's made 100 throws and then he recorded how many meters that his throws traveled to the nearest 10 meters. So no decimals, just every 10 meters is what he's recorded the data for. And we want to assume that he when he throws the disc, it continues in the same proportions. Um, and we want to choose all the answers that apply. Okay, so this is about expected value. I'm going to write just as a review for you, the expected value formula. So it's the sum of all of, in this case, all of the throws of the X values times the probability of that throw. And this is our expected value formula. If you need to review this for the basics of this, I'd suggest going back and looking at some of the previous lessons that we've gone over so far. So here we have what the X values are, but we aren't given the probability in our table. So I'm going to make a new section on the table. Let me zoom in a little bit so we can see this a little bit better. So we'll write the probability of X for all of these values. Now he's thrown 100 throws, so we're just going to write everything over 100. So 4 over 100, 21 over 100, 32 over 100, 35 over 100, and 8 over 100. And we can write these all as decimals too. This is 0 0.04, 0 0.21, 0 0.32, 0 0.35, 0 0.08. Okay, so now we're going to calculate the expected value because the first choice that we have is his next disc throw is expected to travel 32.2 meters. So if we calculate the expected value, this is telling us the expected value of one throw. So let's do that. And I'm going to zoom out a little bit so we have some more room to write here. So for 10 meters, the probability is 0 0.04. And I think earlier I might have said this is X for the throws. That was a mistake. The distance in this case is our X. Uh, for 20 meters, our probability is 0 0.21. For 30 meters, our distance is 0 0.32. 40 meters is 0 0.35. We're just multiplying X times the probability of each X occurring. And 50 meters, the probability of that occurring is 8%. Okay, then we're just going to check all these values on our calculator. We get 0 0.4 plus 4.2 plus 9.6 plus 14 plus 4. And once we add all those together, we get the expected value of one throw is equal to 32.2. Okay, so we can say that A is true. That is our expected value, 32.2 meters. Let's check B next. It says the expected value of Tanner's next 50 disc throws is 2,000 meters. If we want to know the expected value, so this is for A, let's write for B next. If we want to know the expected value for 50 disc throws, we would write this with notation as E50x. And all we're doing is we're multiplying 50 times the expected value of one throw. So 50 times one throw is what we're calculating there. And so the expected value 50 throws is 1,610. And B says it's 2,000. That is not correct. It's not correct for B. Okay, and then for letter C, it says in the long run, Tanner will throw the disc 40 meters more than 4 times as often as he throws the disc 50 meters. Okay, so this one is asking us to examine the probabilities. It's saying to check the probability of him throwing the disc 40 meters. So we'll write that. We'll say the probability of throwing the disc 40 meters is 0.35. And then it's saying that that probability is 4 times as much as the probability of him throwing it 50 meters, which we found is 0.08. So it says it's more than 4 times as much. So there's a couple ways we can do this. We can divide, we can say 0.35 over 0.08, and that gives us 4.375. That's telling us that this is 4 times more. So we have 4 times more of a chance for him to throw the disc 40 meters than 50 meters. We could also just say 0.08 times 4 and then see if that is less than the probability of him throwing the disc 40 meters, and it is. I like this way better. We can get an exact number, 4.375 times more of a chance, or in the long run, um, throwing the disc 40 meters than 50 meters. Okay, kind of a lot of questions to answer on this one. Answer choice D says his next disc throw is most likely to travel 30 meters. And for one throw, we found our expected value earlier as 32.2. And if we round that down to 30, we might say that that's correct. But if we look more carefully at the table here, we can see that when he throws 30 meters, there's a 32% chance that he'll throw the disc 30 meters. When he throws the disc 40 meters, there's a 35% chance that he'll throw it 40 meters. So it's a bit more likely for him to throw the disc 40 meters than 30 meters. So don't use this expected value number for these. Make sure you're checking the table. So this one is false. So the most likely distance thrown would be 40 meters. Okay. All right. The next problem is asking us to solve using systems of equations. And I like this problem because I think it's good to review some algebra with systems of equations, and then also to be thinking carefully about what are we multiplying by and what are these equations representing in terms of units. That way we can think more accurately in terms of um, what our equations and our variables are even representing. So this problem is about somebody who owns a lawn care business, and they researched the size of 50 different lawns. Um, this person, Alma, she remembers that she's expected to take care of 21 acres of lawn for every 6 customers that she receives. She also knows some of this table data below. She knows that with there's 4 customers with 1 acre of lawn, 6 customers with 2 acres of lawn, and 9 customers with 5 acres of lawn. But she doesn't know how many customers have 3 acres or how many customers have 4 acres of lawn. We want to find those missing numbers in this table. So the first thing that we should do here is we should find the expected value of acres per customer. So we'll calculate the expected value of acres of lawn per customer. So for our expected value of that, we had 21 acres for every 6 customers. And if we write that as a decimal, that's 3.5 acres per customer. Okay. Next, we want to find the expected acres for 50 customers. Very similar to what we did in the last problem with the person that threw the frisbee 50 times. We're going to find the expected value for 50 customers. And the reason we're finding for 50 customers is we know that that's our total customers. So now we're just going to write this as 50 times 3.5. Okay, and I'm going to write the units for this just so it makes a little bit more sense about what our equations are representing in terms of units. So we have 50 customers times 3.5 customers, or excuse me, acres per customer. I'm just going to abbreviate there. Now, when we do this, we end up canceling out the customers, and now we know our expected value in terms of acres. So we can say that our expected value of 50 customers is equal to 50 times 3.5, which is 175. Customers and customers cancel out, and we're left with acres as our units. Let me circle our answers for each of these two. Okay, so now we know our expected value for acres per 1 customer and our expected value of 50 customers. Next, let's define our variables. And what I mean by that is, let's figure out what these boxes represent. So we're going to say this is X and this is Y. So I'm going to write that down for later, though, for when we write this in. So we're going to say let X equal number of customers with 3 acres of lawn. And we're going to let Y equal the number of customers with 4 acres of lawn. Okay. Now we're going to get into the systems of equations for this. And hopefully this all makes sense with our units when we do this step. I'm going to write this kind of over here so we have some more room. And we're going to write the total acres equation. Okay, so to get the acres equation, um, this this is kind of interesting, I think, because on the table here it says acres of lawn. And really, we could say I'm going to rewrite this table as this is acres of lawn per customer. And I think maybe it might have been a little more clear if we wrote it that way, but maybe not. That's just what helped me do this problem is rewriting this as this is how many acres of lawn for every one customer there are. Or, yeah, for every one person. So to multiply our units, we're going to write this as acres per customer times customers equals acres. So we're writing an equation for total acres. Okay. Now, when we look at the table, I think this will click and make a lot more sense when we look at these numbers in the table. So for 1 acre per customer times 4 customers, that would give us our total here, but just 4. For 2 acres per customer times 6 customers, that would give us 12. And then this is 3 acres per customer times X customers is 3X plus 4 acres times Y customers is 4Y plus 5 acres per customer times 9 customers is going to equal the total acres that we found in step 2 for 50 customers. Okay, let's write that there. That's fine for now. Okay, now we're just going to simplify this. This is 4 plus 12 plus 3x plus 4y plus 45 equals, excuse me, not 50. That was my mistake. Our total acres is 175. Thought something was a little off there. 175. Okay, so all of this should be 175. Let me finish writing this way also. So we can write a new equation here, adding all those up, and that equals 175. This is total acres. If you wanted to write it in the table like that, you could, if that helps you visualize that a little bit better. Okay, now we're going to simplify this equation. And this becomes 16 plus 3x plus 4y plus 45 equals 175. And it becomes 3x plus 4y plus 61 equals 175. I'm going to subtract 61 from both sides. And we get 3x plus 4y equals 114. And this is for our acres, our total acres equation. Okay, we're going to hang on to that equation, and we're going to build a second equation for total customers. So our second equation, right, for total customers equation. Okay, so for the total customers, that's a lot easier to write. We're just looking at this column in the middle now. So that's 4 plus 6 plus x plus y plus 9. And that equals 50. Just adding together the customers. And then here we were adding together the total acres. And again, we got the total acres by acres per customer times customers. Okay, so now you have x plus y plus 19 equals 50. And we're going to subtract 19 from both sides just to simplify this a bit more. And we get x plus y equals 31. And that's for our total customers equation. Okay. And I'm just going to scroll out and make sure we have enough room here for the rest of this. Okay. Looks like we do. All right. So now we're going to solve the system. You can use Desmos graphing calculator if you want to. You just go to desmos.com/calculator and you can type these in one line at a time and it'll show you where they cross. We're not going to do that today because that's kind of a different lesson for algebra, but we are going to just go over the algebra of how to solve this. So what we're going to do first is we're going to solve for either x or y for either one of these equations. I'm going to choose this equation because it's this most simplified equation that we have so far. So if we write this as, actually, let me write both of these equations again, because this is how you would see them written out as a system of equations. You just see them written like this. And you can solve this with elimination. If you know how to do that, you can solve it that way, or substitution. I'm going to focus on this one with substitution. So we're going to minus y from both sides just on the second one. And we get x equals 31 minus y. Now we know what x is, and we're going to plug in all of this for what x is into our first equation that we haven't manipulated yet. So when we plug that in, we now have 3 times 31 minus y plus 4y equals 114. So now this becomes 93 minus 3y plus 4y equals 114. We're going to simplify, combine our like terms. We get, that's 1y, and this is 93. So y plus 93, or 93 plus y, is equal to 114. And then we're going to subtract 93 from both sides, and we get y equals 21. Okay. Now that we have y is 21, we're just going to plug that back into either equation, top or bottom. And this is probably a review for you, but we're just going over this anyway. So we can plug it into this equation. That's probably the easiest one to substitute that back into. And so now that would be x plus 21 equals 31. Subtract 21 from both sides, and we get x equals 10. And we defined our variables earlier. Let's go back up here and check how we define those again. So we got x is 10 and y is 21. We defined our variables earlier. We said that x is for 3 acres per customer, and y is for 4 acres per customer. So we'll just write those in for x and y. And so this is 10, and this is 21. So now Alma now has the missing data that she needed for the number of customers. All right, so hopefully that was some good review. If you already know how to do systems of equations, that's amazing. That's great. But if you maybe needed a refresher, hopefully that was helpful for you. This last example for expected value with empirical probabilities is a little bit of an easier example. This is a fictitious study, and they want to determine the growth rate in the European Union. They're asking 5,000 adults in the EU how many children they would ideally have. And they have options of 0, 1, or 2 kids. And we have all the data and the frequency table listed here. We want to plot the points that represent the expected sum of the ideal number of children for each number of randomly selected adults. Okay, so I just copy and pasted this from from Khan Academy. If you're working directly on Khan Academy with these, this is a drag and drop kind of problem where you just click and hold the green dot and then drag it to where it needs to go. But we'll look at what the graph looks like at the end here. So we have the frequency and then the number of children here. We still need to find our probabilities in order to calculate the expected value. So the probability for each of these, there's a total of 5,000. And so the probability of someone wanting 0 children is 1,200 over 5,000. And if we simplify that, that's 0.24. The probability of somebody wanting 1 child is 100 over 5,000, which is 2% or 0.02. And the probability of somebody wanting 2 children is 3,700 over 5,000 or 0.74. And you can do the complement rule on the last one if you want to. Okay, so we're going to calculate the expected value for 1 adult. Let me just write that out so we know what we're finding exactly what the expected value means in this case for 1 adult. Okay, so the expected value is equal to x times the probability of x. So probability of 0 kids plus, we're going to do the same thing for each of these, x times the probability of x plus x times the probability of x. And now we're just going to fill in what these numbers are. 0 times 0.24, 1 times 0.02, 2 times 0.74. And this becomes 0 plus 0.02 plus 1.48. So the expected value of 1 adult is 1.5. So you can't really have 1.5 kids, but that's the expected value. Okay, now we're going to complete the table for these different values. So we can write it in a table or actually I'll just graph it for this. So for 1 adult, if we select 1 adult, then that's just 1 times 1.15, which is, or excuse me, 1.11 times 1.5. So that would be there. And I'll show a final graph of this also. So for 1 adult is 1 times 1.5, which is just 1.5. For 2 adults, it's 2 times 1.5, which is 3. So put that there. For 3 adults, that's 3 times 1.5, which is 4.5. For 4 adults, it's 4 times 1.5, which is equal to 6. And then for 5 adults, that's 5 times 1.5, and that's 7.5. Okay, so that would be our graph of the expected value of how many total kids that these adults would have. So we're expecting the expected value of any 1 adult that we select to say that on average they would have 1.5 children. So if we select 2 adults, then the sum of that would be 3 kids. If we select 4 adults, the sum of that would be 6 kids, and so on. And so the pattern continues in this sort of table that we made here. And it's just asking us to graph it. And this is a bit of a more, let me just find the exact graph, what it would look like at the end here. So that would be our final graph. Just put that there. Okay. Next, we're going to look at expected value with calculated probabilities. So this first section that we've done so far is on empirical probabilities, where it gives us the exact values of everything. Now we have to look at theoretical probabilities. And these are calculated mathematically from probability rules and from distributions. Okay, so this person is in a clothing combination contest. This is, it seems like it's a game with combinations of clothes. So Marita, she's going to randomly choose a pair of brown, purple, blue, green, or black pants. Then she's going to randomly choose from black, brown, or green for shirts. And in this game that she's playing, if the shirt and the pants are both a color that starts with a letter B, she wins $10. But if only one piece of clothing is a color that starts with a B, she doesn't win anything. She breaks even. And then finally, under any other circumstance, she loses $20. So we want to know what her expected value is going to be of playing this clothing combination contest game. So let's start by listing out all of the different choices of clothing that she has. So we'll list the clothing choices. Okay, so we have pants to choose from and shirts to choose from. So from pants, she can choose brown pants, purple pants, blue, green, or black pants. It looks like there's 5 possibilities there. And the probability of her selecting pants that start with the letter B, I'm just going to call it B pants, is equal to, let's see, so we've got brown, blue, and black. So there's 3 that start with a letter B out of 5. So that's the probability that she selects pants that start with the letter B. Now we'll do the same thing for shirts. Black, brown, or green. She only has 3 shirts to choose from. So the probability that she selects a shirt that starts with the letter B, I'm just going to write B shirt, is 2 out of 3. Okay, so now we have these probabilities and we can think a lot less about all these colors. So now we've narrowed this down, and so now we can just focus on the probabilities of each. So now we're going to calculate the probability of winning $10. I'm just going to say winning $10. We'll make that in blue. So find the probability winning $10. Okay. If she wins $10, both the shirt and the pants start with the letter B. Now, if both of them start with the letter B, that's the probability of B pants and shirts. Remember, and means we're multiplying our probabilities. So 3/5 times 2/3. That would be the probability that both the pants and the shirt start with the letter B. So that's 6/15, or 2/5. I'm just going to hang on to that answer. I'm going to circle it for later. So that's the probability that she wins $10, which is the same thing as probability of pants and shirts starting with the letter B. Those mean the same thing. So actually, let me just write this at the top here, just so we are clear that that is the same. Those both equal 2/5. Okay, so that's scenario one. Scenario two would be, this is for step three. Our next scenario would be if only one starts with a B, she breaks even. So that means the probability of, we're going to find the probability of $0 or break even. Okay, so that is the same thing as only one starts with a B. So we have two cases here for the probability that only one starts with a B. Okay, so let's write what that means in words first. So if only one starts with a B, that means one scenario one would be that she has pants that start with a B and no shirts that start with a B, or no B shirts. That's our first way that we can have only one of these starting with a B. I'm going to call this case number one. Case number two is just the opposite. Case number two is the probability that she doesn't have pants that start with a B, and she does, I'm just going to say yes, B shirts. She does have shirts that start with a B. That's case number two. So let's kind of try to conceptualize this. We're looking at case one is just, yeah, she has pants that start with a B, doesn't have a shirt that starts with a B. Case two is, no, she doesn't have pants that start with a B. Yes, she has a shirt that starts with a B. Okay, now we're going to figure out what these all are. So for case number one, this is probability blue pants and no blue shirt, or no, excuse me, no shirt that starts with a B, and yes, pants that start with a B. No, I didn't mean to say blue there. Okay, so the probability that she has pants that start with a B is 3/5. And shirts that don't start with a B is 1/3. Just did the complement rule, 1 minus 2/3 to get 1/3. Plus probability that she doesn't have pants that start with a B is complement rule. 1 minus 3/5 is 2/5 times, because we're saying and, the probability of a shirt that does start with a B is 2/3. Okay, so now we're going to just multiply all of these out, and we should get, let's see here, make sure that's all correct. Yep. Okay. And so now this becomes 3/15 plus 4/15. And this equals 7/15. And this is the probability that only one, either the pants or the shirt, starts with the letter B. And when that happens, she breaks even or makes or loses $0. That's the same thing. 7/15. Okay. And then for the last one, we should be able to use the complement rule. Um, but let's see if we can just figure out using these probabilities. So for the last one, we want to calculate the probability of losing $20. And that says under any other outcome, she loses $20. So calculate the probability of losing $20. Okay. So to lose $20, I'm just going to write this in green. I'm going to say probability of, before we said, see, scroll up just a bit. Probability of losing, just trying to keep all my notation the same, losing $20. And we'll calculate what that is. Now, to lose $20 would be the pants don't start with a B and the shirts don't start with a B. So the same thing would be no pants that start with a B and no shirts that start with a B. Okay, we're going to go back up here and find the probability of no pants that start with a B. That's the complement rule. 1 minus 3/5 gives us 2/5 times the probability of a shirt that does not start with a B. Complement rule again. 1 minus 2/3 gives us 1/3. So we get 2/15. And that's the probability that neither the pants or the shirt start with the letter B. Now we should be able to just get that 2/15 by using the complement rule from our first two. 6/15 plus 7/15 gives us 13/15. And then if we add those 2/15, we should be able to get this last answer of the probability of losing $20. So if that saves you some time, you can always do the complement rule for the last bit of these problems. Okay, now we know all of the probabilities for these three situations. So our last step is going to be to calculate the expected value using these three probabilities and the associated dollar amounts of winning or losing these dollar amounts. Let me just write the last one, 2/15. And I'm trying to zoom out. Hopefully you can see that okay. I'm trying to zoom out so we can see all of our data at the same time while we're doing these calculations. So our expected value of playing this game is we win $10 is positive $10, and we have a 2/5 chance of winning $10. Plus making $0, making or losing $0 is a 7/15 chance. Minus $20. Very important. We're losing $20 and we have a 2/15 chance of doing that. If you put plus, you won't get the right answer for this. So make sure you have the negatives where they need to go. So losing $20 minus 20. Okay, so now we're going to add all these together to find our expected value. So we get 20/5 plus, that's just 0, minus 40/15. And we'll simplify this. That's equal to 4 minus, and this becomes 40/15. If we divide by 5/5, we get 8/3. And I'm just using fractions so that way now we can multiply this 4 by 3/3, and we can leave everything in fractions. And that way we get an exact answer. So we get 12/3 minus 8/3. And that becomes the expected value is equal to 4/3. And if we write that as a decimal in terms of dollars, you get $1.33 for our expected value of playing this game. So to conclude for this game, where she could win $10, she could break even, or she could lose $20. In this particular game, she would expect to win $1.33 on average if she were to play the game over and over and over again. So in this case, she would want to play this type of a gambling game or contest. All right, let's take a look at another one where um, we don't really have a possibility of a negative outcome because the amount of winnings are so high for all of these scenarios in our next example. So this next example is about a football team, and they have three different ways um, that they could win these football games and make a lot of money for their football team. So this is about the Wisconsin Badgers. They have two regular season games and one bowl game that's left over in their season. So they have three games to go. And we have these different situations of what could happen. The first situation is if they win all three games, they make $100 million. That would be the best case. The next situation is if they win their bowl game, but they don't win all three games, they make $20 million. So if they win their bowl game, not all three, they get 20 million. And then finally is any under any other outcome, they still win just $10 million. So they've played many games already. They just have three to go. So it says under any other outcome, no matter what happens, they still make $10 million. We also have some more information about these sports analysts that are predicting that this football team has a 60% chance of winning a regular game and a 40% chance of winning a bowl game. Okay, so we have our probabilities for some of this. So we have the probability of the type of game, but now we have to also find a probability of winning all three, winning a bowl game, but not all three, and then it's just anything else that could happen. So let's start by listing out our outcomes, and we'll find the probability of each outcome. So we'll start with the given information, and that was the probability of a regular season win. So that probability is 60%, it tells us at the end there. And the probability of them with a bowl game win is 40%. Okay. Um, and they have two regular games and one bowl game. Okay, now we're going to start with our first scenario, which is the probability of them winning all three. There. That's all right. Just that mark there. Okay. Okay, so winning all three, probability of winning all three games. All right, this is P, win all three. And winning all three is a regular season game, 0.60. Another regular season game, or we could say it as win a regular season game and win a regular season game and win the bowl game. So that would be the probability of winning all three. Pretty straightforward. Multiply all that out, and we get 0.144. That's our probability, or that's this team's probability of winning $100 million. We'll circle that for later. Next, this is the more complex case, is where they win the bowl game, but they don't win all three. And here we have three different scenarios of how this could happen. So let me write out what we're finding here. So we're going to calculate the probability of winning bowl game, but losing. Actually, let me write and instead. That might make more sense because we're talking about probability. So calculate the winning bowl game and losing at least one regular game. Okay, so there's different ways for this to happen. And I'm going to write down all those ways. So we'll write this as case one or scenario one. And this is going to be the probability they win the bowl and lose a regular game, and then they lose another regular game. That's one combination. Another combination, they win the bowl game and they win a regular game. And I probably should have wrote and there also. And they lose a regular game. That's case two. Case three. Case three is, so we have win bowl, lose, lose, win bowl, win, lose. And then the last one is win bowl, and lose regular game and win a regular game. Remember, we cannot have win bowl, win, win as one of these cases because that was already addressed. And this here, where we would just win all three games and get the 100 million. So these are all the different combinations that we can use to find the probability of winning the bowl game and losing at least one regular game. Okay, so now I'm going to write out what these are. Winning the bowl game is a 60% chance. Losing a regular game is, let me see here, winning a bowl game, 60% chance of winning. Okay, so they have a, back here. Okay, so of winning their bowl game is 60%. And of losing their bowl game or their regular game is, I just made a small error here. Let me back up. Let's start over here. So winning a bowl game. So bowl game win is a 40% chance. Probably caught that earlier. 0.4 for winning. Now losing a regular game. To win a regular game is 0.6 as a probability. So losing would be 1 minus 0.6 or 0.4. And then losing again is 0.4. We're going to multiply all those together. And for case one, we get 0.064. For probability of winning the bowl game, again, is 0.4. Winning a regular game is 0.60. Losing a regular game is the complement of that, 1 minus 0.6, or 0.4. I'm going to multiply that. We get 0.096. Winning a bowl game is 0.4. Losing a regular game, again, to win a regular game is 0.6. So to lose a regular game is 0.4 times, or we can think of it as and winning a regular game, 0.6. And when we multiply all of that out, we get 0.096 again. Okay, these are all mutually exclusive. These are all the different cases that we could have. And so we're going to add all of these together to get the probability of winning a bowl game and not all three games. That was our second amount of winnings that we could have, which was for $20 million. Let me color code that a little bit better. Okay, so when we add all of these probabilities together, 0.064 plus 0.096 plus 0.096, when we add all those together, we get 0.256 for our probability of winning. Go back here. I think it said $20 million for that one. Yep. So that's our probability of $20 million. Okay, we'll circle that. And then any other outcome. Last time on the last problem, when we did any other outcome, we actually did the math for it. Let's just do the shortcut for the any other outcome. The any other outcome, I'm just going to write probability of any other for any other outcome is equal to 1 minus our probability of winning all three games minus our probability of winning the bowl game and then not all three games, which is 0.256. So the probability of any other circumstance is equal to that. So we're just going to subtract what those are. I'm just going to subtract our probabilities that we found so far, I should say. And so we have 0.60. That's our probability of winning the $10 million. Okay. All right. That was the tough part, finding all the probabilities for in order to calculate the expected value. So now for our last step, we're going to calculate the expected value. Calculate the expected value of all of these different situations happening. So for winning $100 million, trying to make sure we can see all of this on the screen at the same time. For winning $100 million, we have a 0.144 probability of winning 100 million. Plus winning 20 million, we have a 0.256 probability of winning 20 million. And this team has a 0.6 probability of winning $10 million. And so as you can see, all of these are favorable outcomes. These are all positive values. So no matter what our number is, we know it's not going to be negative and it's going to be a good outcome regardless. But just kind of keep note of that. These are all positive numbers. So this is 14.4 plus 5.12 plus 6. Okay, and then we add these all together. We get a total expected value of $25.52 million. And that is our final answer. If we go back up here, it looks like they want us to write it in millions, I believe. Just double checking here. Yeah. So just make sure you just write the 25.52, and it says nearest hundredth. So that's looks like we rounded to the right amount of decimal places. All right. Our last section is on making decisions with expected value. Um, and in the previous problems, we used expected value mainly to predict long run averages. But in this section, we're now using expected value to compare choices and to make decisions. So the goal is no longer just finding an average outcome, but it's also to determine which option tends to produce the better result over many repeated trials. So we're going to be able to look at two different types of data and figure out what would be the better option to choose from, not just what is the total expected value and looking at empirical data and calculating, but which of the two would be the best option. All right, so this first problem is about a fruit shop and they sell grapes and kiwis. They only sell two kinds of fruit. The fruit shop owner, Gabriel, he puts either grapes or kiwis on sale and he's trying to figure out which fruit that he should put on sale this week. He gets all of his business from people who walk by his fruit shop and they stop in, and he's able to perform market research. And he asks 150 different people if they would purchase grapes, kiwis, or nothing at all if they walked by and grapes were on sale. And then he does the same thing. He asks them, "Do you want to purchase grapes, kiwis, or no fruit if kiwis were on sale?" So he does that for 150 people for each group. So group one, grapes are on sale. Group two, kiwis are on sale. So he's surveying a total of 300 people that are walking by his shop. And we want to find out a few different pieces of information. The first thing we want to find out is what is the expected profit if he puts grapes on sale? And then the second thing is what's the expected profit if he puts kiwis on sale? And then the third one is just let's compare those numbers and see which he should put on sale, kiwis or grapes. Now, so now we figured out how many people he's talking about. I think we can scroll down to this part now. This is data on the profit that he gets from the grapes when the grapes are on sale. And then also he makes profit when kiwis are on sale as well. Um, and then the same thing, profit from the kiwis when the grapes are on sale and when the kiwis are on sale. I think the toughest part about this problem is reading through these tables and figuring out how to interpret them. We also have another table here that tells us the customer choice for if they chose grapes, kiwis, or nothing based on if grapes are on sale or kiwis are on sale. And so I'm going to walk us through which parts of the table that we need to really focus on for each part of the problem. So let's focus on the grapes first. So that's our first thing. We want to find the expected value for one customer, just for one customer when grapes are on sale. And it helps me to color code this. If it helps you, that's awesome. If you're not the kind of person that likes to do color coding, that's fine, but it helps me to just color code some stuff here. So we want to find the expected value or the expected profit per customer. So to do that, we're going to find the probability that the customer chooses either grapes kiwis, or nothing when the grapes are on sale. Okay, so we're going to look at grapes on sale here to find our probability of the customer choosing grapes, kiwis, or nothing when the grapes are on sale. So the probability a customer chooses grapes is 123 out of 150. The probability they choose kiwis is 20 out of 150. The probability they choose nothing at all is 7 over 150. Okay, now we're going to calculate the expected value. And again, this is when grapes are on sale. So I'm just going to, actually, we probably don't need to highlight that again. We're still talking about the grapes, and we've got that highlighted there. So we're going to calculate the expected value. Just write it here anyway. The grapes are on sale. Just so we don't get confused when we start doing the kiwi data. Okay, so the expected value is equal to, um, now we're also going to look at this when the grapes are on sale, our table here. So the expected value is the profit from the grapes when the grapes are on sale is 0.75 times the probability that somebody chooses grapes, 123 out of 150, plus the profit from the kiwis when grapes are on sale, 0.8 times the probability that the customer buys a kiwi even though grapes are on sale, 20 out of 150. And then for the nothing portion, if nobody buys anything, then the profit from buying nothing is just zero. And then we can just, to be formal, we can write 7 over 150 just to write a complete equation for our expected value when grapes are on sale for one customer. Okay, so now this becomes, we multiply all this out. You can rewrite it as a decimal. In fact, I'm going to do that just so we have everything in the same format. 0.82 plus 0.80 times 0.133 repeating, and that's just plus 0. Okay, so the expected value for grapes is 0.615 plus 0.10664. We're going to add these together, and I'm going out a few extra decimal places. Um, it looks like they want us to round to the nearest cent, is what it says for our instructions here. So in order to do that, I'm going to go out a little bit further, just a few extra decimal places than what would be necessary for going out to the nearest cent, just in case. So when we add these together, we get 0.72164. And that's how many cents that we would expect to gain from one customer when we put grapes on sale based on this data. And I'm just going to leave our answer like this for now. And we can round it later, I think, when we need to. So that's for one person when grapes are on sale. Now it says this week 300 people walk by his shop. So now we want to find how much that would actually be for 300 people. And the reason that's why I left this decimal further than just writing 72 cents, because now we can be even more exact. We want to find the expected value for 300 customers or 300 people. So this is E 300x. And that's going to be just 300 times 0.72164. Okay, and that equals 200. Let's see, 300 times 0.72164 is 216.492. And we're just going to, now we can round to the nearest cent. I think that would be an appropriate time now because we don't have to do anything else as far as calculating. So that is our expected value for when grapes are on sale. Let me just highlight it like this one more time, just for so when we go back, we can take a look at this and just reference it a lot easier. Okay, so now we're going to do the same thing, but for kiwis. So we're going to find the expected value for one customer when kiwis are on sale. It's going to be our first step there. So this is part 2. We're going to calculate the expected value for one customer when kiwis are on sale. And I like this problem um, because it shows us a bit of repetition from the first example because we're doing essentially the same thing. Now I'm going to copy this problem actually so that we can not have to keep scrolling up and down. I'm just going to copy this exact same problem down here so that we can see all of our data. Okay. All right. So that's all the data that we need for that actually. So that's good. Okay. So the probability that the customer chooses grapes, kiwis, or no fruit when kiwis are on sale. We're going to focus on these columns next. Okay, so the first thing we're going to do is find the probability. Let me just color code this too. Green for kiwis. Okay. So part A, we're going to find the probability that the customer chooses grapes, probability that they choose kiwis, and the probability that they choose nothing. They don't buy anything at all. So the probability that they choose grapes when kiwis are on sale is 50 over 150. Kiwis is 76 over 150, and no fruit at all is 24 over 150. Okay, then we're going to find the expected value when kiwis are on sale. Okay, so we're going to multiply the profit times the probability. This is profit, and I probably should have wrote the last one like this. Profit times probability, and kiwis are on sale. So the profit from grapes is 0.95 times the probability of grapes is 50 over 150 plus the profit from kiwis when kiwis are on sale, 0.6 times the probability that someone chooses kiwis is 76 over 150 plus the profit from choosing nothing. They don't make any money if they don't sell anything, 24 over 150. Okay. This is just 1/3, 50 over 150 or 0.33. I'm just going to change everything to decimal. No, 0.0667. I'm just going out a few extra places when necessary, just to be more exact, or when we find the expected value for 300 people. Okay, so now this becomes, again, this is the expected value for one person when kiwis are on sale. So now this is 0.31667 plus, and the other, multiply these, is 0.304. Okay, and then we get an expected value for one person of 0.6206 repeating. And again, this is when kiwis are on sale. And that's for, I'm just going to write for one person. When kiwis are on sale. Okay, and now we're going to find out what is our expected value, or what is our actual amount going to be if we have 300 people shopping for fruit. So we're going to calculate the total expected value. And this is just for 3 people, or 300 people, excuse me. 300 people stop in. So we write this as E 300x. Okay, so now that's 300 times 0.6206 repeating. And when we multiply that, we get, let me just double check my answer here, 6206 repeating. We get 186 point 19998 is what I got repeating. So I'm just going to round it to $186.20. I believe if you're typing this in Khan Academy, it's fairly lenient with your final answer in terms of cents, even though it says to round to the nearest cent. I believe it because it says when necessary for this particular problem, that it will accept your answer to the nearest dollar. So it shouldn't be too picky with the pennies, but I always like to just be extra careful and go out a few extra decimal places and then around at the end. It's just usually what I do. Okay, so that's our expected value of 300 customers with when kiwis are on sale. So now we have those two values, and those two values, this value and this value, that goes in our answer box here. So when his profit from grapes is $216.49. His profit from kiwis is $186.20. And now the last question just says, which one should he put on sale? Well, he should put grapes on sale. And that's just our last part of our problem. We make more money. He makes more money when he puts grapes on sale. His profit's 216 versus 186. So this last one's just grapes. Okay. All right, we're going to do a similar problem now where we could, um, I was going to say if we could lose money, but we're not going to be able to lose money in this next problem. But this next problem is about purchasing a virus software. And um, Xavier's trying to decide if he should purchase a virus software. He knows the probabilities of getting these different viruses. And he's trying to figure out if he should buy virus protection or not. So there's 3 different viruses that he could get on his computer. And these are just made up viruses. Maybe some of them are real, but um, it, the software that he's considering purchasing will protect him perfectly from 2 of these viruses. It'll protect him from the Trojan virus and the Pikachu virus if he buys the software. So I'm just going to write the given information for step 1. this. Given if he purchases, he's protected from Trojan virus. Oops. Trojan virus, Pikachu virus. Okay. So that's if he does purchase, but he's still not protected from the ADA virus. There's just so much in this problem. I'm writing out a summary of the given information. Um, he makes a table below also that shows the probability of the cost and repair of these three viruses that are in circulation. We want to assume that he can get at most one virus and that this table is accurate. So we have the type of virus, how much it would cost to repair, and the probability. So we've got a lot of information here to be able to calculate the expected value, but we just have to know, right, our difference between when he does buy the software versus when he does not buy the software, the virus protection software. So we'll write when he does purchase, when purchasing. And again, just color code it. Yes, he bought the virus protection. Okay. So the probability that he gets the virus, he could still get the virus if he purchases it, but for some of these viruses, if he does get it, the virus protection will remove it from his computer. So we're still going to write that he has a probability of getting these viruses, even though he's protected from receiving these viruses. So when he's purchasing the virus protection software, the Pikachu virus probability is 0.2. Trojan is 0.2. And the ADA probability of the ADA virus is 0.1. 0. Okay, so that's the probability. So the A, we're just writing the probability for these of getting the virus. Okay, for part B, what we're going to find is we're going to figure out the repair costs for each. For each virus. Okay, so for the Pikachu virus, when he does purchase it, he's covered. So the Pikachu virus is 0. Doesn't cost him anything. If he gets the Trojan virus, also protected. Doesn't cost him anything. But if he gets the ADA virus, he still has to pay $300 because his software doesn't cover that virus. Okay, so now we're going to find the expected value of purchasing virus protection. Okay, so when we purchase virus protection, we now have the probabilities of each virus and the cost of each virus. So the expected value is equal to, we'll do the Pikachu virus first. That would cost him $0, and he has a 20% chance of getting that. If he got the Trojan virus, that would cost him $0, and he has a 20% chance of getting that. And if he got the ADA virus, that would cost him $300, and he has a 10% chance of getting that. Now, you might be thinking that's all of our equation, but we have to also include in here how much that he paid for the virus protection. And if I left that out in the beginning, I apologize. The problem at the top is saying he's trying to decide if he should spend $25 to purchase this software. So it costs him, he does have a cost, which is $25. We're writing all of the expected value in terms of cost. So we're saying that the cost is positive. So we are not subtracting 25 from this. We're adding $25 to our cost. This is the cost added, or the cost of the software. So we're just adding that to the cost. Okay. So now we have 0 plus 0 plus 300 times 0.1 is 30 plus 25. So our expected value for the cost of this is $55. And that's if he does purchase the software. That's how much that he's paying to protect his computer from viruses in general if he purchases the software. Okay, now we're going to figure out the expected value of if he does not purchase the software. So I'm going to write this as part 1. And here's part 2. Does not purchase virus protection. And we'll color code this again for when he does not purchase the virus protection. It's like computer's taking a moment here. Okay. So it does not purchase virus protection. And this is a little more straightforward because we have the probabilities of each virus, and we also have the cost of repair. So we're just going to multiply these values from the table for part 2. So this is actually, I should say that's step 3. And then, so now we're going to multiply all of these. So to find we're looking at the probability that he gets each virus. I'm just going to write it down, but it does match what's on the table. So I'm just writing down what we're doing for our steps. Probability of getting each virus, which is written right here. And then the cost, he would have to pay for the Pikachu virus. He would have to pay for the Trojan virus, and then he would still have to pay for the ADA virus. If he had no virus protection, that's how much that it would cost him. So B, we're just going to say the cost of each virus. And then for part C, we're going to calculate the expected value of not purchasing the virus protection. And so if he doesn't purchase it, he doesn't have to pay the 25. So we don't have to worry about adding anything extra onto there. We're just going to figure out now if he got the Pikachu virus, that would cost him $400. He has a 20% chance of getting that virus. If he got the Trojan virus, that would cost him $200, and he has a 20% chance of getting that virus. If he got the ADA virus, that costs him $300, and he has a 10% chance of getting that virus. Okay. So again, we're not adding anything extra. We're just using the total cost of each virus times the probability. This is the easier solution to do because we're having to pay for each of these viruses, and we're not buying virus protection. So we're just using all of what's on our table here to find the expected value. Okay, when we multiply this out, we get 80 plus 40 plus 30. And this is equal to 120 plus 30, which is $150. This is if he does not buy it. Okay, so I'm going to write down what our answers were here. This was $55 if he did get the virus protection, 150 if he did not. And then the best payoff in the long run, remember, this is how much that he's having to spend. So he's having to spend $55 if he does purchase virus protection. He's having to spend $150 if he does not purchase virus protection. So the better deal definitely is yes, he should purchase virus protection. All right. This last example is um, it is with expected value, but it's for a game flipping a coin. And I think this is a great last example because we're going to review some key ideas in probability, such as the fundamental counting principle and how to use combinations with probabilities, which I think is a great tie-in to some previous lessons. So here's our last example with expected value. Your friend offers you a choice to play two different coin games with him. The first game, he says that you're going to flip four coins. If you flip two or fewer heads, he gives you $1. Otherwise, you pay him $3. The second game, he says that you're going to flip five coins. If all five of them are heads, he'll give you $100. Otherwise, if they're not, you pay him $4. And we just want to figure out what the expected value is from the first game, what the expected value is from the second game, and then figure out which of these games should we play to maximize our profit. Okay, so we're going to separate this into game one and game two to solve these. So the first thing we're going to do is look at the game one outcomes. So the game one outcomes, we're just going to write down all of the given information here. So we're going to figure out or determine the game one outcomes. All right, so for game one, we have four coins, and there's two possibilities for each coin. So we can either get heads or tails, and we're going to use the fundamental counting principle to figure this out. So there's two possibilities for each coin, and we're going to flip four coins. So the fundamental counting principle, it tells us that we're going to multiply the number of possibilities times the amount of trials that there are. There's four coin flips. So we're going to do 2 times 2 times 2 times 2, which is equal to 2 to the fourth, which is 16 possible outcomes. So that means that there's 16 different ways that we could flip these four coins and getting different orders of heads, 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 tails, tails, heads, heads, tails, heads, tails, heads. And we're going to actually write out what all these possibilities are in a table. And it's going to take us a little bit of time. But then I'm going to show you a shortcut method using combinations that I think that we've learned this in the beginning of the year. But I always like to try to write the table data out when there aren't too many outcomes. 16 outcomes is getting a little close to there being quite a lot of them to go through, but I still think it's possible to do. So we're going to write the outcomes, the number of heads, and the result for all 16 of these possibilities. Um, and again, we win the game if we get 0 heads, 1 head, or 2 heads. That's our probability of winning. I'm going to write that to the side. Probability of winning is equal to the probability of 0 heads plus the probability of 1 head plus the probability of 2 heads. So we're just defining what it means to win here. Okay, so for an outcome, for our first outcome, we're going to say we get all 4 heads. So number of heads, we have 4 heads, and we have to have 2 or less to win. So our result is we lose. The next one, heads, 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 tails. There's 3 heads there, and we lose. And it might take you a little while to write all these out. Just try to find a pattern that works for you. Right now, I'm just doing 3 heads, or 4, 3, and then write all the ones that have 3 heads, all the ones that have 2 heads, all the ones that have 1, and so on. So this one has 3 heads, and we would lose also. 4 is heads, tails, heads, heads. 3 heads, we lose. Okay, tails, heads, heads, heads. 3 heads, we lose. Okay, tails, tails, heads, heads. This one we have 2 heads, and we would win. Okay, this one is tails, heads, tails, heads. And we win. And we're almost halfway done with our table. I know it's a little bit tedious here. Heads, tails, heads, tails. And we have 2 heads, and we would win. Heads, heads, tails, tails is another combination. 2, we would win. Heads, tails, tails, heads is the next one. Win. Tails, heads, heads, tails. Win. And you might be able to find a table of this online if you just look up how many outcomes, if there's 16 outcomes for a toss. You might be able to look this up, but probably not, because this is a very unique situation um, for whether we win or we lose. But if you just wanted to know the outcomes for the 16 possible outcomes, you probably could find something like that on Google. You could find that online, I bet. Tails, heads, tails, tails. And that's one. And we would win. Tails, tails, heads, tails. And that's 1 head again. We would win. And this is tails, 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 heads. 1, and we would win. And then the last one is if we got all tails. 0 heads, and that's still a win because that's 2 or less heads. Okay. All right. So now we have this. You might want to take a screenshot of this to save it, or if you want to look it up yourself, you can. But I think it's probably going to be helpful if we can take a look at this while we're working on these here. Okay, so let's divide this up again. So if we win, that's 2 heads or less. If we lose, that's 3 heads or more. Okay, so the probability of winning is 0 heads. plus the probability of one head plus the probability of two heads, because those are all different ways that we could win. So let's count all these up. So probability of one head is 1 over 16. The probability, or zero heads is 1 over 16. For one head is 1, 2, 3, 4 over 16. And the probability for two heads is 1, 2, 3, 4, 5, 6 over 16. And I'm going to show you how to do this with combinations in a second. But now we're going to look at the probability of losing, probability of three heads, probability of four heads, and that's as many as we can have. So that's the probability of losing. So probability of three heads is 1, 2, 3, 4 out of 16. Probability of four heads is just 1 out of 16. Okay, now we're going to do some quick review with combinations. So with combinations, we can write combinations n choose r, which is written like that. And we can write this as n choose r is equal to x, where x is the, uh, the different ways to get r heads and n flips. Okay, so really all we have to do for the combinations for these is we're saying there's n is equal to 4 because we're flipping the coin 4 times. And then R is how many heads there are, the number of heads. So you can get these same answers by writing combinations. So this, if you are more familiar with this method, you could even skip writing out all of this table. So to get the 1 for the 1 over 16, we already found the 16 is from 16 possible outcomes from the fundamental counting principle. But to get the 1, that's just 4 choose 0. So we write it 4 choose 0 over 16. To get the 4 is 4 choose 1 over 16. To get the 6 is 4 choose 2 over 16. I know we're kind of running out of room there, but hopefully you can see that okay. So you can write this as 4 choose 0 or 4 choose 0, like that. So that's just the notation for the combinations. And this is in your calculator, you can find combinations in your calculator. And we also went over the formula in some previous lessons. This one would be 4 choose 3 over 16, and this one's 4 choose 4 over 16. So that's how you can mathematically get those from not writing out the information on the table and just using the combinations. Okay, so I'm going to erase this part, and then we're just going to look at the probability of winning versus the probability of losing. So the probability, we're just going to add these together now. Add the total to find the probability of winning. So the probability that we win game number 1, which has these constraints of flipping a coin flipping 4 coins and getting 2 or less heads, we win $1. Otherwise, if we lose, we pay $3. So the probability of winning, we're going to add all these together. 1/16 plus 4/16 plus 6/16 is 11/16. Same thing for over here. We're going to add the total probability that we lose this game number 1, given those constraints we mentioned a few times already, is 4/16 plus 1/16, which is 5/16. Okay, now that we have our probabilities for these, we can finally calculate the expected value for game number 1. Okay, so I'm just going to circle these or actually put a box around them because this is the most important part of our data. In order to calculate our expected value, we have to know the probability of this. So for game number one, this is step two now, we're going to calculate the expected value for game number one, for game one. Okay, and for game one, it tells us on our information here under the instructions for our given information, it says if we win $1. If we lose $3. At first glance, it looks like, well, we're going to win more often, so that might be a good thing. But let's take a look at really what it's going to be. So if we win, that's plus $1. If we lose, that's negative $3. So the expected value is equal to 1 times 11 over 16. So we have 11 over 16 chance of winning $1 plus negative $3 times our probability of losing $3 is 5 over 16. I did plus negative 3. You can also write minus 3. Either way is okay. Just make sure you're denoting that we're losing $3 with a negative there. Okay, so now we've got those probabilities. We can zoom in a little bit more to find out our expected value for game number one. So this is 11 over 16 minus 15 over 16. And here we get a negative value. So that's negative 4 over 16. And our expected value, if we change that to a decimal, our expected value is equal to negative 0.25. So our expected value is we're going to lose 25 cents per game for game one. All right. So far, not a great strategy to be playing this particular gambling game with these rules. We would lose 25 cents every time we play this game if we kept playing the game over and over and over again. So the odds would not be in our favor to play game one. So let me write that down for game one. Your expected return rounded to the nearest cent, negative 0.25, negative 25 cents. Okay, game two, hopefully this goes a little bit faster. Um, so this was all for the game one outcomes. For game two, let me copy this and then we'll just kind of scroll down here and we'll paste it so that way we don't have to keep going back and forth and we can zoom in a little bit better. For game two, we're going to flip 5 coins. And if all 5 of them are heads, we get $100. Otherwise, we have to pay $4. So we're going to determine the game two outcomes. Okay, so for the game two outcomes, we have 5 coins, could be heads or tails. We're going to use the fundamental counting principle again. To find our total possible outcomes. And so we could have heads or tails. So we have 2 possibilities for each coin flip. So that's 2. Then there's 5 coin flips. So that's 2 times 2 times 2 times 2 times 2, or 2 to the 5th, which is 32 possible outcomes. Okay. So you might be thinking, well, now we have to write this table again instead of 16 of them. Now we have to figure out 32 of them, and I have to write out all the heads, tails combinations. That's not true. You don't have to do that. You can use the combinations method that we did earlier. In fact, if we read this more carefully, it says if you flip all 5 heads, you win 100. Otherwise, you lose $4. So there's only one way to win. So to win is if you did heads, 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 and heads. That's the only way to win. So there are 32 possible outcomes. So the probability of winning is equal to that one way out of 32. The probability of losing is 31 out of 32. It's the complement of the probability of winning. 1 minus the probability of winning, or 1 minus 1 over 32. And just to do maybe a quick proof with the combinations, let's take a look at how we get these just to make sure that it lines up with our rule that we learned about for combinations. So if we win, we would say we have 5 coins and we get 5 heads, or 5 choose 5 over 32. And that does equal 1 over 32. So let me just put the equal sign there instead of an arrow. So those are equivalent statements. Now, if we lose, that equals to, we get 0 heads, we get 1 head, we get 2 heads, 5 choose 2, 5 choose 3, and then 5 choose 4 over 32. These are all the ways that we would write our combinations for if we lost. Okay, and then if we type this in our calculator with the combinations, we get 1 over 32 plus 5 over 32 plus 10 over 32 plus 10 over 32 plus 5 over 32, which also equals 31 over 32. So that's our probability of losing. And I just wanted to just clarify that you can write this out with combinations if we didn't get very lucky with our game number 2 that tells us that there was only one way to win. So that's how you would do it with the combinations. That way you don't have to think about so much all of the writing out the table. So using the fundamental counting principle, that's our possible outcomes, our denominator for our probability, and then combinations is the numerator for our probability. Okay, so we have the probability of winning, 1 over 32, probability of losing, 31 over 32. Now we're going to calculate the expected value for game number 2. Okay, so if we win, we get $100 for winning. And if we lose $4. Okay, so our expected value for game number 2 is equal to $100 winning. We have a 1 over 32 probability of winning $100, plus we actually lose, so let's say plus -$4, and we have a probability of getting -$4 or losing $4, 31 over 32 probability of losing that $4. Okay, now we're going to add these together. and find our expected value for game number two. So this is equal to 100 over 32 plus -4 times 31 is -124 over 32. Our expected value for game number two is -24 over 32. And we get, as a decimal, our expected value is -0.75. Or we're going to lose 75 cents for game two. And that's every time that we play the game. That's what we would expect on average, to lose 75 cents per game. So that for part two, we're going to write -0.75. And this first one was -0.25. We'll just write that again there. -0.75 if we lose. Okay, now it says your friend is willing to play both games for 30 times. If you want to maximize your return, what should you do? Play game one all 30 times? Well, if you did that, that would be you lose 25 cents times 30 times. So in this case, you would lose $7.50. So that's probably not good. You're going to lose money doing that. If you played game two 30 times, that's 75 cents times 30 times. That means that you would also lose, you would lose $22.50. If you played a mix of those games, kind of, well, the mix doesn't really explain what that mix is, but it looks like either way we're going to lose. So to maximize our expected return, I would say answer choice D, refuse to play either game.